Titration is a technique when we react acid with bases and we want to find the concentration for one of them. We have the concentration of one, we want to find the concentration of the other. So what we do is what we call titration. So it's used to determine the concentration of either the acid or the base. How do we do it? It's, after all, a reaction between an acid and a base. For titration, this is the titration setup in here. So what you need is a burette. This is called a burette. It is a graduated, like a graduated cylinder, but it is very accurate. It runs from different volumes. It can be from 0 to 25 or 0 to 50. The most common burettes are from 0 to 50 mils. Okay, so it starts from 0 from the top, and it goes all the way to the bottom over here, which is going to be 50 mils. And this is the capacity normally of the burette. So what you do is you go ahead and you fill your burette with mostly your base solution. Okay, so in the burette you fill it with the base solution, and mostly it's a solution that you already know its concentration. And then in a beaker, you go ahead and you fill it with your acid. So see, it's a reaction between an acid and a base. So this one's going to be an acid solution. As I mentioned, it's either one of them that you don't know its concentration, and it's most probably the one in the beaker that you don't know its concentration. The one in the burette usually is what you know the concentration for. Um, So the idea for the titration is that every mole of base that I dispense from the burette is going to go ahead and add with the mole of the acid that is found in the solution. So we're going to keep adding the base in there, and the base is going to keep reacting with the acid until there is no more acid in the solution, right? So once there is no more acid in the solution and you add another base drop, then your solution is going to turn basic. But how would you know if it turned basic? Well, you need to add something which we call an indicator, as we mentioned earlier. So indicator changes color. Before you start your titration, you prepare your acid solution and you add a couple of drops of the indicator. Indicator will have a certain color in acidic solution, and then when the solution turns basic, it will have a different color. And this is when you know that you've reached moles of base are equal to the moles of the acid. This is called the end point of the reaction. So the end point of the reaction is the reaction where the you have no more acid in the solution, and this is when you added an extra drop of the base and the solution turned into a different color. So it's called the endpoint. The endpoint has to do with the indicator. So it's when the indicator changes color, then this is going to be the endpoint of the solution. And then when you reach number of moles of acid are equal to moles of the base, this is called the equivalence point is reached of the solution. This means that you have as much base as that of the acid. Normally, the equivalence point is reached before the end point, because remember, the end point is reached when you add that extra drop of the base in there so that the solution will turn basic. So you would pass the moles of the acid equal to the moles of the base. So again, when you do titration, you start by dropping or adding the base drop by drop into an acidic solution. Make sure that you have an indicator in the acid. Normally, we use phenolphthalein indicator, which is colorless at the beginning of the acid, and you keep adding the base. Every mole of the base you add to the mole will react with the mole of the acid until all the acid is gone. So once all the acid is gone, you've reached your equivalence point. Moles of acid equal moles of the base. But you won't know until you see a color change. So that extra drop that you add from that base will change the color of the solution for phenolphthalein indicator from colorless to pink. Why pink? Because phenolphthalein is pink in basic medium and it is colorless in acidic medium. So it's going to change the color of the solution. Once the change of the color of the solution is there, then you would know, okay, I need to stop now adding the base because now I've reached a solution where all the base reacted with my acid. That's it. So I've reached now my end point. And this is what you do over here. You just go into the burette and see how much base did you use. And from that volume, you can simply go ahead and calculate the concentration of your unknown, which is going to be the concentration of the acid of the acid. So let's have an example over here. Okay, so it says that what is the concentration of HCl solution of 25 ml of the solution is a neutral, if 25 ml of the solution is neutralized by that much volume of that much concentration base. First of all, I know that this is a titration reaction. Why? Because I am reacting an acid with a base. This is what titration is. So you're doing a neutralization. So what is a neutralization in here? You are actually neutralizing. You are reacting an acid with a base. It's called a neutralization reaction. Okay? So again, reacting an acid with a base, it's a neutralization reaction. They need the concentration of the acid. So let's lay down our given in here. So they need the concentration of the HCl. We don't know the concentration of the acid, but this is what we are given. We are given the concentration of the base, which is equal to 0.30 molar. We said that the base, we put it in the burette, and the acid, we put it in the flask. Okay, so the base has a certain concentration. Volume of the base. See, I've used that much volume of the base to neutralize the acid. So I already know the volume of the base that I used, so that number of moles of the acid are equal to moles of the base. This is the equivalence point. So the volume of the base, this is the volume of KOH, that is equal to 40.0 milliliter. Now, because it is a neutralization reaction, this is what you need to write down. So you say at equivalence, because they're telling you it's a neutralization reaction. So if it's a neutralization reaction, then you reached equivalence and you reached moles of the base are equal to the moles of the acid. So at equivalence point, moles of the acid, they are equal to the moles of the base. Good? And I know that the concentration is equal to the moles divided by the volume, right? So I can develop a mole equation and I can say, okay, the moles are equal to the concentration multiplied by the volume. So this means that if I'm talking about the moles of the acid, then it means that the concentration of the acid multiplied by the volume of the acid, that is equal to the concentration of the base, because moles is equal to the concentration multiplied by the volume of the base. Okay, the base is the OH. So I already know the concentration of the base. They gave it to me, 0.3. I know the volume of the base in there. Okay, so I know that. I don't know the concentration of the acid. This is what I need. And the volume of the acid, it's given to be 25 mils. It says that what is the concentration of HCl solution if 25 mil of the solution, so 25 mils of acid. So I am given that the acid is 25 mils. So that is given already. So let's go ahead and put the equation. I know now the concentration of HCl. You can write it like this, or you can write it as a concentration of HCl. Okay, it doesn't matter. Both are the same. That is equal to the concentration of the base multiplied by the volume of the base divided by the volume of the acid. Just make sure that your volumes are the same unit. It does not matter what unit, but just make sure that they are same unit. So the concentration of the base is 0.3 molar in there. Okay, I know that molar is what? I always like to write molar as moles per liter just to remind me that the volume here is in liters, okay? But honestly, you don't need to change the volumes of the base and the acid into liters because the mil and the mil will cancel out. So I would have 40.0 mils. So don't even bother to change that. Just leave it because the mils, again, they're going to cancel out divided by 25, and that is going to be 0.48 molar. Let's have another example. This is similar to number 36 in your homework. So I am given a 25 mil. This is the volume of the acid. Hydrochloric acid is HCl. So I am given HCl. This is the volume of the acid. Okay. This is titrated with that much concentration base. So this is going to be a titration again. Um, Problem where you're reacting an acid with the base. So I'm given the volume of the acid. I am given the concentration of the base, and I am given the volume of the base that was used from the burette to reach a neutralization of the acid. So I use that much volume from the base to reach the neutralization. So now it's asking you about the concentration of the HCl. It's kind of like similar to the question above there. So it's the concentration of the acid times the volume. Again, you can write the concentration as a C, or you can write the concentration like this. I mean, it's just the same idea. Okay, so it's the concentration of the acid times the volume. This is going to be for the acid, so we're going to put both of those for HCl and both of those for NaOH. Okay, so what you need is the concentration of the HCl. So let's go ahead and put the equation. Concentration of the HCl, that is equal to the concentration of the NaOH multiplied by the volume of NaOH and then divided by the volume of the HCl. You guys, you have everything in there. So you have the concentration of the NaOH. This is 1, 2. This is moles per liter multiplied by 21.68. This is how much I used from the base. And originally in the beaker, I had that much of the acid. Here you go. You cancel those out, and your answer is 0.0444 molar. Let's have another example. So what is the concentration of chloride and calcium ions in 2 molar solution of calcium chloride? Now, this one is not a titration reaction, okay? So I just need the concentration of calcium chloride. This is an equation where calcium chloride solid dissociate in the solution. It's a simple dissociation. So I just need to write it so that I can write the balanced equation. So I have calcium chloride solid. I am dissolving this in water. So when I'm dissolving this in water, this is not an acid, you guys. It's just a dissolution of calcium chloride. So that calcium chloride is going to change into its individual ions into Ca2 plus aqueous plus 2Cl minus aqueous. Just make sure that you have a balanced equation. Okay? Now the question is that they need the concentration of the chloride and the calcium ion in 2 molar solution of calcium chloride. So I'm starting with this guy over here, okay? I'm starting with a solution of this guy to be 2 molar. When it dissociates, this one is a solution, right? So when it dissociates, it's going to turn into ions. The ions are going to have the same concentration, but you got to pay attention to the coefficients in there of the ion. So the Ca2 plus still have the same concentration, which is 2 molar in there. And I do have 1 calcium ion, so 1 mole of calcium ion. So I'm just going to go ahead and multiply the 1 mole times the 2 molar, This is 2 molar calcium ion. And I know now the concentration of the Ca2 plus is going to be 2 molar once this dissociate. Now, for the Cl minus, the solution, original solution is going to be 2 molar. You multiply this by how many moles do you have of this ion? I have 2 moles of the Cl minus, so that is going to be 2 times 2 molar. So I know that the concentration of the Cl minus in the solution is going to be 4 molar. So the question here, to answer the question, I would say the chloride concentration in the solution, this is the chloride concentration in the solution. This is a solid. You dissolved it in the solution. It turned into ions. So the concentration is going to be depending on the number of moles of these ions in there. So I would say that the chloride concentration in the solution is 4 molar, and the calcium concentration in the solution is going to be 2 molar. Okay, these are various problems in your homework, similar to the problems in the homework that we are solving. This is not an acid-base titration. So what is the pH of a 1 molar solution of nitric acid? Okay, I'm given a concentration, right? Now, nitric acid is what? They did not give me the direct concentration of the acid. So please pay attention. They gave me the concentration of the solution of nitric acid. That was different than the problems that we worked with earlier for the pH. With the pH, we were given the direct concentration of the H plus, but here we're given the concentration of the solution. So when you're given the concentration of the solution, you have to change that solution into its individual ions and know what's the concentration of the H plus. So pay attention to this. So what I would do here is that I would look at the nitric acid and I would say, okay, nitric acid is going to dissociate into H plus and into NO3 minus, okay, into its acid and its conjugate base. So that is going to be the acid, and that is going to be the conjugate base. I'm sorry, conjugate acid and conjugate base. So I know to calculate the pH, I need minus log concentration of H plus, right? I am given the concentration of the HNO3 solution. I need to get from this, I need to get the concentration of this one. So it's always equal to the concentration of the solution multiplied by the number of ions. So here I do have 1 H plus, 1 mole of H plus and 1 mole of NO3 minus. So I go ahead and I say, okay, the concentration of H plus is going to be equal to the number of moles multiplied by the 1 molar. Okay, and then the concentration of the NO3 is equal to 1 mole times 1 molar solution. You guys, I don't care about NO3, I care about H plus, so here it's going to be 1 molar. So that's the final concentration of H plus, it's going to be 1 molar. So I come over here and substitute the concentration of H plus, which is going to be minus log 1. I know log 1 is equal to, log 1 is equal to 0 in this case. So the pH is equal to 0. pH 0, this means that it is going to be acidic. Okay, let's have another example. What is the pH of 0.034 hydrochloric acid solution? You guys, again, I'm given the concentration of the solution. I need to find the concentration of H plus in that solution. So here it happened again that H plus is going to, or HCl is going to dissociate into H plus and the Cl minus with a 1-to-1 mole ratio. It's not necessarily always 1-to-1 mole ratio, okay? So I'm starting with a 0.034 molar HCl. Then the ions over here is going to be 1 times 0.034 molar. And here's going to be 1 times 0.034 molar. So a solution of 0.034 molar HCl will dissociate into 0.034 molar H plus and 0.034 molar Cl minus. Since I need the pH, then pH, I know it is equal to minus log concentration of H plus, right? So that is equal to minus log concentration of 0.034, and that is equal to, these two are going to be equal to negative 1.5. So my answer is going to be positive 1.5. By looking at the pH, I would know that the solution is going to be acidic. The last topic is buffer. So what is a buffer? Buffers are solutions that they do have the ability to resist the pH change when you add additional acid or base to them. So let's say, for example, if you have a beaker, and in this beaker you do have a buffer. So we said that buffers are made up of two components. They are made up of an acid part and a conjugate base part. Okay? So if we go ahead and add a base to the buffer, in the buffer we already have a conjugate base in there and we already have an acid. So what's going to happen is that if we add a base, the base is going to go ahead and react with the acid component. It's going to keep reacting with the acid component to maintain the pH of the solution. So the pH of the solution will not change because I do have an acid component that can react with that base, of course, at a certain extent. So I cannot add too much base in there. I need to add enough, just to be enough to match the amount of the acid that is found in the buffer. Because if you consume all the acid part in the buffer, and you add an additional base, then you start changing the pH of the solution. So you got to pay attention. So you keep adding the base is going to react with the acid component of the buffer to maintain the pH. Or if you go ahead and add an acid, the acid is going to react with the conjugate base part of the buffer and the pH is going to be maintained. So again, a buffer solution is made up of two components, acid and its conjugate base. And it's normally we use it to maintain the pH of the solution whenever an extra amount of acid is added or an extra amount of base is added. Okay. What are examples of buffers? These are matches for buffers: acetic acid, sodium acetate. So this is going to be the acid, and this is going to be its conjugate base. So this is considered to be one buffer solution. Acetic acid is this formula. Guys, you don't have to memorize. Sodium acetate is this formula. So whether we write it like this or we write it like this, both are going to be sodium acetate. Both of these are going to be acetic acid. Another couple for buffer is the formic acid and sodium formate. So it's the acid and its conjugate base. So whenever you see stuff like that, this means that we are working with a buffer. Buffer has its own equation, and that is represented by a Henderson-Hasselbalch equation. It's simply a relationship between the pH of the solution, the pKa, the concentration of the base, and the concentration of the acid. Okay. Buffer capacity, this is the amount of either the acid or the base that can be absorbed without causing a significant change in the pH. They can be absorbed by what? By the buffer itself, because buffer has two components, acid and base. So again, you are adding external acid, external base to an original buffer solution. So whatever base you add is going to react with the acid component of the buffer up to a certain extent. So the buffer will stop the solution from changing its pH. Same thing with the acid. So whatever acid you add, that is going to react with the conjugate base part of the buffer, and the buffer will maintain the pH of the solution. If you add, you guys, if you go ahead and you add more of the acid than what you have in the buffer, then this means that your solution over here is going to come and turn acidic. So the pH is going to change. So this is why buffer has a capacity. So the Henderson-Hasselbalch equation is conjugate acid divided by the conjugate base. We do have all of these relationships in there. We already know pKa is minus log Ka. This is an old equation. So if we go ahead and say, okay, if the conjugate acid and the conjugate bases are the same, then in this case, we are talking about log 1 Log 1 is a 0, then we say that pH is equal to pKa. This is a special case for the Henderson-Hasselbalch equation when these two have the same concentrations.